Hello students, good morning, good evening and good night, depending on which time you are going to observe this lecture. Welcome to the 8th lecture on solution chapter. Before going to discuss the relevant topic in this chapter, let us have some discussion on the 7 lectures, that is the previous 7 lectures in which we have discussed different topics in the solution chapter. First, in the lesson number 1, we have discussed about the very fundamental things in the solution chapter, like the definition part, definition of the solutions, what is solute and what is solvent, and what is binary solutions, and different type of solutions. Different type of solutions, that is on the basis of the physical state of the solution. The physical state of the solution is basically depends on the physical state of the solvent, because solvent is the major part of the solutions. There is 2 components of the solutions. Solvent is the major part and the minor part is the solute. So there is a different type of solution that we can observe, we can understand, that is the solid solutions, liquid solutions and gaseous solutions. And also in that lecture we have discussed about another very important thing, to express the different types of methods about the concentration, that we express the concentration in different ways, that is the molarity, molality, normality, formality, mole fraction and parts per million, and also the percentage weight, percentage mass, that is percentage by volumes, that we have discussed in that first lecture. The second lecture we have discussed about the different types of relationships, that is the relationship between the mole fraction and molality, mole fraction and molarity, and between the molarity and molality. And this type of relationship will help you to solve many numericals, different types of numericals that may appear in your examinations. Then in the lecture number 3, we have discussed about the solubility of solid in liquid. In that lecture we have discussed in detail what are the factors that are going to influence the solubility of the solid solute in the solvent, that is the lattice enthalpy, that is the type of solvents, all we have discussed. Impact of temperature, impact of pressure, that we have all discussed in this lecture. In the lecture number 4, we have discussed about the solubility of the gas in the liquid solution, and in that respect we have discussed about the Henry's law, and this law that we understand how the pressure above the solution is going to influence the solubility of the gas in the solutions. In the lecture number 5, we have discussed a very important thing, that is when there is a solution and the solution, 2 components of the solutions is the volatile components, and at that time what will be the vapor pressure of that solution, that we have discussed in this lecture. That it is basically, we have also connected with the Raoult's law. The Raoult's established the fact that the vapor pressure of the solution is basically depends on the mole fractions of the component in the solutions. And we have also understand in this lecture also how do you able to calculate the fractions, that is the compositions of the vapor, that is the 2 components, how do you able to calculate. In the lecture number 6, that is also a very important thing that we have discussed, that is depending on the Raoult's law, we can classify the solution in terms of your different ways. That is the ideal solutions, non-ideal solutions. Also, we have discussed in that lecture number 6, that is the azeotropic mixtures. In the lecture number 7, we have discussed the when we add some non-volatile substance, non-volatile solute in a volatile solvent, at that time what amounts is vapor pressure, and we observe that vapor pressure is basically lower than the vapor pressure of the pure component that we have discussed. And in that regard also we know with this reduction in the vapor pressure in the solution, there is a correlation between the different properties of the solutions. That is number 1, so relative lowering of the vapor pressures that we have discussed in these lectures. So this is the 8th lectures. We are going to discuss the another one very important colligative property, that is the elevation of the boiling point. Okay, so in this lecture, the heading of this lecture is so this is the lecture number 8, the elevation of the boiling point that we are going to discuss. It is also a very important colligative property. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So in this lecture we will going to discuss one very important thing, that how there is a, we already understand when we apply some non-volatile substance in the solutions and in the solvent, and it will be preparing a solutions, and that solution having their lower vapor pressure, and this lower vapor pressure will going to affect, going to influence the boiling point of the solutions, that we are going to discuss in these lectures. To understand this, we have to understand one very basic thing that we have already learned in our class 11, that when we increase the temperature of the solution, the vapor pressure of the solution going to be increases. That can be easily understand from this graph also. Temperature, the y-axis it is the vapor pressure. So what it looked like for the pure solvent. For the pure solvent, it looks like this. So for the pure solvent, it looks like this, that you can see that as we increase the temperature, the vapor pressure of the liquid goes on increasing. So we can write the pure solvent. It is pure solvent. As the temperature increase, the vapor pressure will going to increase. Now, this pure solvent will boil when its vapor pressure is the atmospheric vapor pressure. Atmospheric vapor pressure, atmospheric pressure. When the vapor pressure of the pure solvent is equal to the atmospheric pressure, and that is 1.013 bar. 1 atmospheric pressure is 1.013 bar. This is the pure pressure, and at that time the temperature in this case, suppose it is TB0. Suppose it is TB0, it is the boiling point, the boiling temperature of this pure solvent. So at this, when the temperature of the pure solvent has been increased to the this temperature, that is TB0, at that time the vapor pressure of the pure solvent will be equivalent to the atmospheric pressure. That is why water boils at 100 degrees Celsius, or we can say this is 373.15 Kelvin. At that point, the vapor pressure of the water is 1.013 bar. That is why it boils. So when the temperature has been increased to TB0, suppose TB0 for a pure solvent is this. Now in the water, suppose we are add some non-volatile substance, that is 1 mole of non-volatile substance we put, that is the sucrose. Sucrose, that is non-volatile substance, we put in the water. At that time, what is going to happen? We know that due to this inclusion of the non-volatile substance in the pure solvent, the vapor pressure of the solution is going to be decreases. So what will be the vapor pressure for the solution? So vapor pressure of the solution, the curve for the vapor pressure of the solution will be like this. Naturally, the curve will be below the pure solvent. So this will be like this. So you can see a very important thing. At the temperature in which the pure solvent boils, at that time the solution, you can write this is a solution. At that time the solution is not going to be boiled because it is having the lower vapor pressure on account of we add a non-volatile substance. So it will not boil at the temperature. To make this solution boils, what we have to do? We have to increase the temperature so that its vapor pressure can increase, and when it reaches to this point, you will see from this curve that the vapor pressure of this solution is equal to the atmospheric pressure, that is 1.013 bar, and this point it will going to be boiled, and temperature of the boiling point of the temperature has been increased to where this is TB. Suppose this temperature is TB. So you can easily understand that there is a elevation or increase of the boiling point, that this elevation of the boiling point is this. This is, we say, delta TB. It is, you can write the elevation of boiling point. Elevation of boiling point. Okay. So how boiling point going to increase with the inclusion of the non-volatile substance, which basically being attributed due to the lowering of the vapor pressure of the solutions. So this is called the elevation of the boiling point, and that is TB. So we can write TB, delta TB is equal to TB minus TB0. Here you can write that TB is greater than TB0. That is, the solution, the pure solvent, having lesser boiling point than a solutions. So this is called the elevation of the boiling point. You can understand the very practical example I can give, that when you put 1 mole of solute, 1 mole of sucrose in a 1 kilo of the water, what we find? We will find that there is the water boils at pure water boils at 373.15 Kelvin. What is solution? Solution with sucrose. Solution with sucrose. It boils at 373.54 Kelvin. So you can see there is a increment of the temperature boiling point of these solutions. So this is the elevation of the boiling points, and this elevation of the boiling points, like the relative lowering of the pressure, it is depends on the number of particles, not on the nature of the particles. So it is a, we can say it is a colligative property. So it depends on the number of particles. So we can write this depends on the number of particles. So this is a colligative property. Now for the dilute solution, now we want to quantify this elevation of the boiling point with some other constants or some other concentration of the solutions. It is on the basis of experiment, it is found for dilute solution. It is observed the elevation of the boiling point is directly proportional to the molar concentration of the solutes, or we can say molality of the solutions. So we can write this delta Tb is equal to Kb into M, and Kb is a constant that comes in this equation. This is called it can be called, Kb is boiling point elevations constant. It is called boiling point elevation constant. Boiling point elevation constant. Number 2, this is also called molar elevation constant. Molar elevation constant. Another term, ebullioscopic constant. Ebullioscopic constant. It has 3 names: ebullioscopic constant, molar elevation constant, and boiling point elevation constant. Is Kb. Kb is basically the characteristics of the solvent. We can again write Kb is characteristics of solvent. It depends on the solvent. Like different solvent will have the different Kb. As for example, water has the Kb is 0.52. Carbon tetrachloride has Kb, it is 3.18. So this time you can understand the Kb is characteristics of the solvent, and it depends, it varies with this type of the solvent. So we understand the Kb, we understand the elevation of the boiling point, how Kb comes, and this Kb can also be correlated with another thing, that is with the universal gas constant, with molar mass, and it is that Tb 0 square divided by 1000 into delta H vaporization. So this Kb you can also relate it with this equation, where you can see it is the R is the universal gas constant. We can write this R is universal gas constant, M1 is molar mass of solvent, and delta H vaporization is enthalpy of vaporization. So we relate this Kb with other things. So we relate with Kb with this equation, that is a universal gas constant, molar mass of the solvent and enthalpy of vaporizations. Okay, I think this is clear to you, that how the elevation of the boiling points with the inclusion of the non-volatile substance in the volatile solvent has been occurred, that you can easily understand from this, and how do you quantify these changes, that is, it is directly proportional to the molality of the solutions, and it is also correlated with all the factors. Now we want to correlate with the molar mass of the solute, because from this elevation, by measuring the elevation of the boiling point, you can able to calculate the molar mass of the solute, that we now discussed. This relationship, that is delta TB, that is elevation of the boiling point, is equal to M into Kb. M is the molarity. Suppose W2 gram of solute, having molar mass of M2 dissolved in M1 gram of solution, and this effect, this, when we add the solute in the solutions, it creates an elevation of the boiling point, that is delta TB. So from this we can able to calculate the molality of the solutions. Molality we know, moles, number of moles divided by solvent, amount of solvent in kilos, kilo of solvent, we can write this, kilo of solvent, or you can write solvent in kilos, solvent in kilo. So here moles, number of moles, that we can easily calculate, W2 gram of solute having the molar mass M2, so we can write W2 divided by M2, and W1 gram of solvent, this is the solvent, W1 gram of solvent means W1 we have converted into the kilo. So it will be coming W2 by W1 into 1000 into M2. So from this we get this relationship. That we can, this is the relationship that we can get, that is M Now we put this M, by putting this M here in this equation, M is here given W2 into 1000 divided by W1 into M2 into Kb. So M2, that is the molar mass of the solute, you can write W2 by W1 into 1000 into delta TB into Kb. And if we know See, by making an experiment, say simple experiment, that by putting one, suppose you do not know the molar mass of the solute, by making an experiment and knowing this elevation of the boiling point due to the inclusions, due to this solute, whose molar mass we do not know, and if we know all these values, that is W2, W1, TB and KB, we can able to calculate the molar mass of the solute. We can able to calculate the molar mass of this solute, that is in M2. Okay, by knowing the weight of the solute, by knowing the weight of the solvent and the elevation of the boiling point, and also by knowing the KB. If you know all those things, and you can easily able to determine the molar mass of the solute. So this is a very important relationship. By knowing the elevation of the boiling point, we can able to calculate the molar mass of that solute. Okay, so this is from this colligative property, that is elevation of the boiling point. One thing that we have to remember, the elevation of boiling point is a colligative property, but boiling point is not a colligative property. Elevation of the boiling point is the colligative property, because it depends on the number of particles, not on the nature of the particles, right? So that is all for today's lecture. In this lecture we have discussed one of the very important colligative property, that is the elevation of the boiling point of a solutions when we put some non-volatile solute in the solvent. Hope that is all the points clear to you. If you have any doubt, you can comment in the comment sections. Thank you very much for watching, and next video we will discuss another two important colligative property, that is the depression of the freezing point or the osmotic pressure of the solutions. Thank you very much for watching.